many others, with the aim of facilitating access to quantum technologies to people who, like you, look into this fascinating world. Quantum computing is an emerging discipline and a potentially disruptive technology to which companies are beginning to give importance as a key technological agent for the future. Okay, it is a technology that, because it is centered on computing, necessarily affect all scientific and technical disciplines, and directly or indirectly all the products and services that companies offer currently to society. Okay. Quantum computing changes, in his essence, the engine of the information society in which we live, by proposing a computing model that radically breaks with previous technology. This new technology has the capacity to address computational problems that current computers are not expected to be able to deal with, such as the design of new materials, of the analysis and synthesis of drugs. On the other hand, quantum computing has changed the approaches to information security by breaking the current protocols of public key cryptography. This fact, with enormous repercussion in today's society, is undoubtedly one of the main reasons why companies are interested in quantum computing. In this context, the demand of experts in quantum technologies and quantum computing is expected to increase considerably in the coming years. To conclude, I would like to thank Amazon for their kindness in organizing this seminar on the quantum technologies. And I would also like to thank the interest shown by all those attending this event, and wish them a personally enriching experience. Okay, thank you very much, Agustin.
Thank you, Jesus. Now it's time for Juan Moreno from Amazon to talk to everyone and to explain and maybe give you your overview of the workshop and maybe some presentation about it. Thank you, Juan.
Excellent. Thank you, Agustin. Thank you very much for cooperating with us in this initiative. We are very excited to finally get off the time zone of the Americas and being able to extend this event to more areas of the world. It's a total pleasure for me to do this event with you guys. Only because you are Spanish and I'm Spanish, so it's great to see that my country is having a growing interest on this technology. So this is very exciting. I'm personally very happy about it. It's going to be a very exciting couple of days. We have 3 hours ahead of us today and 3 hours tomorrow as well. And what we want to do is to give you an introduction to quantum computing. So we will be covering all the basics, but also we are going to get hands-on experience. You will be able to work with quantum computers, with simulators, and you will have exposure to different technologies within the quantum computing world that you will be able to touch with your fingers in a working environment. So my only advice is that you try to get the best out of it, ask as many questions as you want, get engaged. We bring the best of the best to deliver this training. So just take advantage of it and be active. For this first day, I'm honored to have here my colleague Jagadish Pusapati. He goes by Jax. He's one of our experts, and he's going to be delivering this first day. I'm going to be here in the background answering questions and helping you, but he's going to be our main speaker for today. Jax.
Yeah, nice meeting you all. I am one of the solution architects based in London, so closer to most of the participants here. And I thank Juan for waking up early. So it's 6 a.m. for him today, and he's supporting this session. And we have a few more colleagues who can help out if we need any help during the labs. I'll get started. Is there anything else before we begin, Juan?
Go for it, Jax. The floor is yours.
Thank you. Let me try screen sharing now. Is it visible? Is it okay? Loaded?
Perfect.
Thank you. So today we are going to go through initially introduction of what quantum computing is. I will start from scratch, as Juan mentioned. We'll go into the basics and we'll describe where we are today in quantum computing, what are the use cases. Then we'll jump on to setting everyone up for the hands-on labs later, so everyone gets comfortable with their accounts and their lab environment. And then we'll jump back into a presentation where we go through quantum computing initiatives within AWS, different types, and what we do in different we are doing in different areas. Then we'll have a short break, and then we'll have an introduction to Amazon Braket itself. So this is our quantum computing service where you can get hands-on. I'll go through some demos, and then we can dive straight into actually hands-on running your tasks and circuits on simulators and QPUs. That's the plan for today. And tomorrow we'll continue with a bit more advanced topics on hybrid jobs and quantum annealing. That's for tomorrow. Right, let's get started. And in between, if you have any questions, please ask in chat or even unmute yourself if you can, or you can interrupt me some way. Who will be keeping an eye on the chat. So if you have any questions during the talk, please interrupt and then we can have the discussion as well. Right. What is quantum computing? So quantum computing is a different way of processing information. So in digital world, we have been using transistors and semiconductors for a long time and solving problems. It has come a long way in the last many decades. But quantum computing is using a different way of solving these problems. So it's using some of the laws of quantum mechanics to do this processing. Because the way these quantum computers are processing information is very different. There are some kinds of problems that can be solved in a different method. So it's not like quantum computer will speed up every kind of processing. No, it's suitable for some specific use cases and will provide speed up for some of those problems. And there are compelling evidence that some of the problems cannot be solved efficiently in classical computers. When you say classical, everyday digital computer now has become a classical computer to contrast it with the quantum computing. So these class of problems are generally, when the number of inputs grow, the problem size increases exponentially. Those are the difficult problems that we struggle with digital computers. So some of these subset of problems can be solved more efficiently on quantum computers. We'll go into a bit more details on the structure of it and all that. But first, I want to focus on where we are in the industry. So even though we have been talking about quantum computing for decades now, only in the past few years we have advanced technologically from building a hardware side of things to take it to a level where we can use it for real life applications. Building a quantum computer is not an easy task. We still don't have a perfect large enough quantum computer to run real life problems. So the main challenge comes from the way the subatomic particles that are used in quantum computers interact and how we interact with them. So they very easily change state or cohere. They're very sensitive. So if you have seen popular pictures of quantum computers, you would have seen they're operating like some types of superconducting ones operate in a very low temperature. This is because they interact with the environment at higher temperature and they decohere. So the coherence is a problem. So apart from that, there are other engineering and scientific challenges in building quantum computers, because while they are interacting with those elements, we want them to talk to each other and we want to interact with the elements. but we don't want anything else to interfere with them. So that's a typical and a difficult challenge in actually building a quantum computer. So there are scientists and researchers working in developing different methods and approaches to solve this problem. So that is one. And because quantum computers are, or what we call this is noise, so where the, the the qubits don't do what we expect them to do. So those issues can be solved in multiple ways. One is fixing the hardware itself to so that it doesn't have less and less. And also we can build some logical like error correction and mitigate against those errors. So both of those two areas are in active research. And there are lots of discoveries and papers being published at a very high rate. So this is an interesting time to be in this field. And so within the next few years, we should start seeing more and more advancements. But why is there so much interest? So to give some comparison, we talked about some difficult problems on classical. So there are some class of problems where even with the fastest supercomputer, it can take hundreds of years, even thousands of years to solve a particular problem. But there are some within those problems, there are some when as the problem size grows, it can be solved in a quantum computer in a fraction of time, say seconds or minutes, depending on the size. So if you're following the media, you would have aware like a few years ago, Google came up with an announcement saying they have achieved this, they have proved what we call like quantum supremacy, where they have solved a problem on a quantum computer using their chips, which would have taken many years on a classical computer. We also have to note, like even the classical computers and digital computing is also improving continuously. So we are finding different ways of improving in a classical world as well. So it's more finding the right solutions that will benefit from quantum is also becoming a moving target. And more recently, Xanadu, one of the photonic quantum computers, they also came up with a solution where they have proved the one of the difficult problems that will be impossible in the classical world. What kind of problems can be solved using quantum computers? So quantum computing, as we talked about, we said it's involving very small elements and it's suitable naturally for atomic research, or in the sense, very minute properties of proteins, not proteins, molecules and others. So that's one area, but it's not just related to pure science research. The applications of these problems are across multiple industries. So one example is like optimization problems. They are not specific to physical or natural world. So it's applicable to multiple industries. So in financial services, in manufacturing process, in energy and gas sector. So the optimization problems can be solved in multiple ways. There are many paradigms of solving this within quantum computing. We'll look at a few tomorrow. And also the next area is machine learning. So now we are seeing more and more quantum machine learning, both to using quantum computers as a additional helping for building quantum neural networks, and also applying machine learning techniques to quantum circuits to improve the quantum circuits as well. That's the two facets of machine learning within quantum computing. And the last one is on the chemistry side. That's where the initial focus was on, and this more and more developments of like drug discovery, finding medicines, and also material research, next generation materials, more efficient. All that is being possible using new algorithms using quantum computers. So it's essential that we spend more effort in this area by starting early. Some of these advanced problems can be tackled for end customers who can understand the potential of this technology. We need more and more people spending time on this so that we find more and more useful algorithms in this area. So that's an introduction. So now let's switch to setting up the hands-on environment. I'll put this. So what
I
will
can do it for
be,
you, Jax.
okay, have you got the code? Yeah, okay.
Yeah, I got it.
Sure. So once you go into that, so we'll be using an internal Amazon service called like Event Engine, where you'll be using our this service to access. So once, sorry, once Juan has shared a link on the chat. So if you all can go and click on that link, you should get this terms and conditions page. If you go and
Make it a
accept
little bit
terms and
bigger, Jax.
conditions, make it bigger, did you say?
Yeah. Great.
Yeah.
Thank you.
So go into this and click on email one-time password. And that should ask you for an email address. And if you type in your email address, this can be any email address. And you should get a passcode in a few seconds or within a minute or so. Please message in chat if you're having any issues accessing the link, or if you don't get the passcode in a few minutes or so. For some email addresses and domains, it can take a bit longer, but yeah. Even I haven't got it yet. So.
All right. If someone has not received the passcode at this point, would you mind to please +1 in the chat for those of you who didn't receive the passcode yet? If I didn't receive it, I will type like this. Okay, Perminder, thank you. 3, 4, 5. All right, let's wait a little bit more. So make sure that everyone is at the same point. You are, in
Yeah, you
terms of the
will get
organization,
different
go
team
ahead,
IDs.
Jax. Sorry, go ahead.
Sorry. I saw some messages in chat. So the event ID should be same for all of them, but yeah, the team ID will be different. There are multiple teams created. Yeah, that's okay, Gabriel. Sorry, Yuvan, you were saying something, I interrupted.
I was just addressing exactly the same as you. Too many cooks in the kitchen, my friend.
Next to make sure everyone logs in.
Usually this stuff is a little bit slower at the beginning because we want to make sure that everyone is in the same point. But don't worry, as soon as everyone has their lab configured, we will be able to make it more dynamic and we will go a little bit faster. It's just, this is the critical step. For those of you who said that didn't receive the code yet, if you already received it, please let us know so we can know how many people more or less are still pending. All right, I think we can move forward, and great. You can move forward and I will take care of any pending problems here in the chat, Jax.
Okay. So once you're logged in, just make sure. Sorry, lost my screen. Once you're logged in, so if you click on this AWS console, so if you are already logged in to an AWS account using the same browser, you may get a logout message. Otherwise, you should get this screen here. So clicking this open console will open an AWS console and give access. But for now, if you can click this copy login link and store it away, it's a very long URL. So this is your specific one. So tomorrow, if you're coming back or if you do see your browser, you can click that login link, go directly instead of going through this whole journey again. In case you lose it, if you give the email address, the same email address, you will still end up in the same account and you'll have that mapped. But that saves this copying this login link saves the trouble and you can get to your account specifically. So the link will be something very long like this. That is fine. Okay, once you're done, please click on Open Console. So we are doing this early just to create a notebook so that that can be happening in the background while we continue the presentation. So we'll come back to the console and explore different options. If you're new to AWS, we'll go a bit more in depth in a while, after a bit. But for now, once you're here, I'll like you to access the Braket service and create a notebook, and that'll create in the background. So to access Braket, once you're in the console, either you can click on Services, go down to Quantum Technologies and click Braket, or you can just simply search from here and click on Amazon Braket. Once you're here, if you click on Notebooks, you'll end up here and you have a Create Notebook Instance button. So, sorry, before that, I need someone background noise.
Yeah, Ernesto, I cannot unmute you. Could you please unmute yourself? Sorry, could you please mute yourself, Ernesto? All right, you can continue now.
Oh, they've dropped. Okay. So this is the next couple of steps is only for some people because we're using five members in a single account. One of them, so whoever gets there first will get to do this, and others will not be able to do it. It's more enabling permissions. So if you go to permissions and settings, sorry, before we go into the notebooks, there are a couple of things. So one is accept terms and enable. So here, until you enable this, you will not be able to use the hardware providers. So if you click accept terms and enable in one of your accounts, and then switch to execution roles and create the service linked role. So this service linked role enables Amazon Braket service to access other AWS resources on your behalf. We'll get to that in a bit. So for now, if you go and click this create service link role, someone has already done this for in this account I'm using, so that's fine. If we refresh, it should show green here, and also click this verify link and create default role here as well. So make sure these two are green in your account. Please refresh just in case someone has created for you. That's fine. Yeah, so this should be enabled, and these both should have uh, green messages here. Okay, so that's done. Once that's done, come back to the notebooks and we'll kick off creating a notebook. So this managed notebook from Braket service. Once you create it, it creates a Jupyter notebook environment with all the libraries installed and the examples get already cloned in, so you don't have to do anything. Once the notebook is created and is available, you can start running your program. So there's nothing else to do apart from this one. So here, give it a name, your name or something that you will do, because once you create, there will be other notebook instances in the account. Make sure you use your notebook you created, and to avoid any disturbing others' work or others disturbing your work. I'm just using mine. So if there is, this has to be unique in a region, but the service adds some suffix if this is not unique as well. So here, this is the key. Pick, create a new role for IAM. Leave that as default. You can leave rest of them as default for now, and click create notebook instance. So this is pending. So now if I see it's already in my account. There's another notebook being created. So this will take about between 5 and 8 minutes. So once you're done, we'll give it a couple of minutes for everyone to create, and then we'll jump to that. So there's a question in the chat. When would we want to use a different machine size for notebooks when working on Braket related tasks? So the machine size depends on what you're trying to do. So here, for what we are going to do in this lab today, we don't need a big instance because most of the tasks we are doing are simple Python parts, and then we'll be submitting jobs to either the simulator or to the QPUs. The machine size depends on what you will run locally. For example, in some cases where you want to do some local optimization, you can even spin up a GPU instance where you do the local machine learning part on the classical machine learning part in the local notebook instance, and then submit jobs to the QPU or the simulator across the bracket. So that's one use case where if you want to do heavy classical processing, then you can choose a bigger instance. There was a problem during role creation. There's an error. Can you retry doing that status? Yeah, once it gets to pending status, yeah, that's all for now. Because there are multiple using, maybe it's the same time. If you hit create notebook, if it goes beyond the rate limiting, so there could be some. So if you retry in a minute or so or a few seconds, if it works, that's good.
Seher, if the problem persists, just ping me your account number that you can find in the top right corner as you are in the
That's the account
console.
number.
Yeah, and I'll see if there
You
is
can see screen.
anything different that is not working.
Is anyone not yet created. We can +1 if you have not yet created a notebook. Then we'll look into that. If not, we'll continue in a minute.
Seems we are good.
Okay, let's continue then. Look. Okay, now let's go into us at AWS. What are we doing in this area? So we are humble about these technological and scientific challenges, and at the same time, very excited about their potential. So as we have talked about this, the industry is at the research phase and there's a lot of development happening. It might take years before we see like first commercial applications of quantum computing, but it's never too early for our customers to start exploring and be at the forefront of these innovations. So one of the core aims was to democratize quantum computing and give access to multiple technologies. That was the core driver behind it. Now we'll jump into Braket as an end. So I'll quickly say what Braket is, but then we'll cover about the other three. So Braket is a fully managed service. It's designed for experimenting and developing quantum computing algorithms. We'll look at other pillars initially. So first one is AWS Center for Quantum Computing. So this is our research in collaboration with Caltech in Pasadena. So one of our aims is to create a quantum computer, a superconducting version. So we announced it in December last year. So we're working on building a superconducting-based quantum computer. Our focus is on both noise mitigation and error correction, so creating logical qubits and using different technologies. So we have a number of leading researchers working at the Center for Quantum Computing. So we are focusing on quantum algorithms and hardware and also near-term applications. While quantum computing continues to be a major area of investment and progress, both academic and industry-wise, it's only one component. So once the quantum computers are available and we need to be able to network them together and connect them together and create a quantum network. So a couple of months ago, we announced AWS Center for Quantum Networking. And a couple of weeks ago, we announced a collaboration with Harvard University on developing this research. So this area is very early in the process. So quantum networks will leverage some technologies that are already deployed for modern optical communications, lasers, fibers, and detectors and repeaters. So instead of strong laser beams, quantum networks need like smaller photons and single photons and use those as building blocks to connect the devices together. So the use cases are will enable advances in privacy, security, and also for in encryption areas. So this is going to be very useful in those. So this is a very early stage for our Center for Quantum Networking, and there's more to come from this area. The next one is Amazon Quantum Solutions Lab. So this is one of our professional services offerings. So here we work with customers on a collaborative research engagements. So this is not just focusing on quantum computing, but we have leading experts in quantum computing, machine learning, and also high performance computing. This program is meant to identify like the most promising applications and also dive deep into the customer use cases and see where quantum computing could be useful, how they can leverage existing classical techniques and HPC and ML to solve their problems they're facing, and also get them quantum ready. So find those interesting quantum inspired algorithms and start learning quantum algorithms and how that will be applicable in the future. So our QSL team, Quantum Solution Lab team, they work backwards from the customer initiatives and help build them the solution and also enable their internal expertise to be ready for the future of quantum computing. And we also have many partners and startups that are focused on quantum, and they're building their services and solutions on AWS using Braket. There are many use cases, mainly around optimization and chemistry and machine learning, and they are working across multiple industry vertical as well. So, sorry. So now we'll focus on Braket. So Braket is a fully managed service. It makes it easy for building and testing new quantum algorithms. We have simulators available for rapid testing. We'll dive into each of these in a bit more depth. You can access it using Jupyter Notebooks. We have SDK, and also you can use CLIs to interact with it. And on running your actual algorithms on QPUs, you can access multiple quantum computers from different technologies. And you can also combine both classical processing along with quantum processing. And you can combine these and run more sophisticated algorithms by leveraging the wider Amazon ecosystem as well. Let's start with Braket architecture. Like many of the services, it is API driven. So all the Braket services are configured through API. On the console, we can see, so the way you access Braket itself is using managed notebooks or local IDE or through the console. At the core of the Braket service, we have simulators and quantum hardware. Simulators. So we have simulators available both on the local. When I say local, when you install the SDK, it installs a local simulator, which will run actually on, if you're doing it on your laptop, it will run on your laptop. But if we have spun up a notebook instance, the simulator will run in that notebook instance. So, but this is, if you, just one thing to key to note is the Braket SDK, you can download and run it on your laptop. If you're only using the local simulator, you don't even need an AWS account. So you can play with the local simulator and understand the quantum technologies and algorithms, and you can play with it completely free of cost just using the SDK. But the local simulator obviously is limited because it can only do so much because of the available compute on your local machine. So it supports up to 25 qubits. And it's really useful for fast and convenient for prototyping and getting your way around. And it also has like two types of modes within the local simulator. You can also simulate noise using the local simulator and also a state vector simulator. Those are the two that are available with the local simulator. Now coming to managed simulators. So we have three different types. SV1 is a state vector simulator. So this supports up to 34 qubits. So this stores the full wave function state, and it applies sequentially applies the gate operations as you run the circuit. It stores all possible states of your circuit throughout your runtime, and this is it depends the number of qubits determines how fast your simulation runs. This is the most popular one, which we have been using for some time. And the next one is TN1. It's a tensor network simulator. So if you, this kind of encodes your quantum circuits into a structured graph. So the nodes are qubits themselves and quantum gates, and they just represent the connections between these gates and our qubits. So this is suitable for quantum circuits that have like sparse connections. So it's not suitable for every type of circuit. It depends on how complex it is. What happens is when you submit a circuit to this, it goes through two different phases. It rehearses whether it can find an optimal way of solving this, embedding it in the graph. And if it can find, then it will go into a construction phase and actually execute it. So this, because it tries to rewire your gates and qubits in a optimized way, it can fit in more qubits. It supports up to 50 qubits. And the last one is density matrix simulator. So this one we added earlier in the year. This supports noise simulation. You might ask, why do you want to simulate noise? We thought we don't want noise. But as you see in real world, you'll see the real QPUs, the hardware ones, do come with noise, and they have noise. So we have to kind of need to know how to deal with them. So each device comes with particular noise characteristics. So if you're writing algorithms and testing in simulators, you need a way to know how will it be impacted when you have noise in them. So this density matrix simulator helps to simulate noise and helps you understand your algorithms better when you're going to run it on a noisy QPU. Right. Next, we are going to look at the physical QPUs or quantum computers. So we provide access to multiple QPUs and different technologies. We have 5 different providers today. So first one, D-Wave, it's based on superconducting technology, but it offers a different type of quantum computing. It's called quantum annealing. So it is not gate-based. So it's not considered a universal quantum computing, but this annealing is suitable for a specific type of problems. So it's generally optimization or a minimization problem is what is programmed using quantum annealing. We'll not go into that today. Tomorrow we have a dedicated session to go into the details of quantum annealing. So we'll cover that tomorrow. The other 3 are all gate-based, and Rigettian OQC or superconducting-based qubits. IonQ uses trapped ions as a technology. But all these are gate-based, as we said. So they use different methods to encode your qubits and build the gates and how each qubit interacts with each other. So the connectivity and how the qubits interact are different in different technologies. So when we go into the console, we'll have a look at those as well. But all these 3 are gate-based. And this one we added recently. So this is from Xanadu, a quantum computer called Borealis. This is using photonics to build as an underlying technology. So photonics-based ones are slightly different. So they don't use qubits. Qubits have discrete states, 0 and 1. We'll come into those in a bit, but the photonics ones, they used continuous variable mode. So they used 216 Q modes. So the Q modes are equivalent of a qubit in a gate-based superconducting-based quantum computer. So here, this photonics-based one is capable of arbitrary computation, but it implements a specific protocol known as Gaussian boson sampling. So Xanadu ran a Gaussian GBS technique and have used to claim computational advantage over classical methods. And they have published a paper, and one of those examples is available as part of the examples notebook. You can run yourself, you can learn this and run these as well. During these two workshops, we'll not be going into this particular technology, but you have access to the notebooks you can try out on your own time as well. The fourth different type of quantum computer is programmable Rydberg mode atoms using neutral cold atoms. So this is announced. We are expecting that in the platform sometime soon. So this uses a different technology again. It uses neutral atoms instead of ions, and it's more suitable for like analog Hamiltonian simulation. So it's more simulating physical quantum mechanical systems. So that's the typical use case we will see. So this will be available soon, and we should be able to look into that as well. Right. Once we have, as part of the Braket service, we looked at simulators, hardware, and next we want to focus on different other AWS services that Braket uses. So CloudWatch for monitoring, so you can observe the results of your tasks, and if you run multiple jobs, you can get those task metrics as well. And Event Bridge is used for notification, so you can use that for triggering events based on your task status when the tasks are submitted or finished. And S3 is our Amazon S3 is our storage service. So this is object storage, and Braket uses S3 to store the results. And like with any other AWS service, we have IAM permissions. These are identity and access management for controlling who has access to what resources. So here specifically, you can set up, if you're using a company, you can say, so this particular team is only allowed to use simulators. So they are restricted simulators. You can check those specific permissions. And so that's available to access to QPUs, access to simulators, and also using different like S3 buckets. So you can separate two teams into different buckets, and they're only able to write to their bucket. So the team-based access control can be configured as well. And lastly is the KMS service. It's used for data protection, encryption for all the results that you have stored, or if you're spinning up the Jupyter notebook we saw, so that can be encrypted as well using KMS keys. And also networking side of things, if you have any strict networking requirements, you can run Braket in a completely private environment as well, like internally. Obviously, the QPUs, if you're going to access QPUs, they are outside AWS network, so you still need to get out of AWS network to get to the QPUs, but you can apply restrictions that are required for your company's policies as well. The three different methods to access. So we have spun up the managed notebooks. Hopefully, by the time we finish, they'll all be ready for us to access. You can access the Braket console. We'll look into that in a bit, where you can look at the task status, submit jobs, look at the QPU details when they will be available, and a local IDE where you can take your favorite IDE, Python-based environment. You can install the Braket SDK and start exploring the quantum world as well. Talking about the SDK, so the Amazon Braket SDK is an open source Python library. It's available on GitHub. It's designed and to make it very intuitive and fairly straightforward. We'll look at some of this in a bit. So you can design and build quantum circuits. You can submit tasks and jobs to devices and simulators. You can track and monitor their executions. And it also comes with the 2 local simulators we talked about earlier. And we also have extensions for Braket SDK. So one of them is PennyLane. PennyLane is an open source Python library for differentiable programming. So it's very useful for quantum machine learning, and it can make more efficient ways of running your QML jobs. And there are examples of using PennyLane, and we'll look at that, maybe one example tomorrow as well. And if you've been working with quantum computing for some time, you would have definitely come across Qiskit. And we also have a Braket extension for Qiskit. So it's called Qiskit Braket Provider. I think this is the right time. Maybe it's better, David, to talk about it than me. So he's one of the contributors to this Qiskit Braket Provider. Is David on the line? Do you want to talk about it, David? I
He's
still
definitely
see.
there.
Yeah, he was there earlier. I can't see him in the list.
I can see him.
Okay.
David.
Can you?
Let me see. Let me check the permissions again to make sure that everything is okay.
Do you see him in the list?
Yeah, I can see him here. Oh, maybe it's in the. Oh, it's in the people who left. Okay, it's in the list, but in the people who left. Okay, so he's not with us. Pity. Well, we will cover for him then.
Yeah, because maybe when he joins, he can talk a bit more about his experience and what he has done as well. So
That's
there
right.
are examples of using Braket Cascade provider. And so what you can do is if you already have a Cascade program, you can, by importing the Cascade Braket provider, you can submit those Cascade circuits to Braket, both simulators and QPU, and also local simulators. And it's not just simple circuits. You can also, there's something called a quantum instance within Qiskit, which you can leverage to use even like QAOA type of programs and QML type of programs on Braket. Just double checking if David has joined again. No, I can't see him.
If he joins later, we will give him a chance.
Yeah, we'll get him just, yeah, sure. Okay. Right. So I've lost the screen now. Right. Let's go into the console first, and let's give a demo. Before I just want to show around the console so you're familiar with it, especially if you're new to AWS. If I can find the right window, there you go. Right, at least in the account I am sharing with others, all the notebooks are up. We'll not go into the notebooks yet. Let's first focus on the Braket console itself, what you can do from here. We already looked at permission settings, and there's nothing more to look into that. So let's start with the dashboard. We'll go into this, we'll take a short break, and then we'll come back for the hands-on workshop. Let's see where we go from there. So here, this is relatively a new one, the dashboard itself. Here you get access to look at announcements, the links to documentation, and also the notebooks. And if you have created jobs, you'll see some jobs as well. We look at jobs tomorrow, what they are, and we'll be creating some. And you can set your preferred devices. So I'll do that. You can select a particular device. I'll choose Oxford Quantum Computer. So it gets added here. So that's So if you are interested in a particular device, you can add it and you can get all the information in one place. Next, we'll look at the devices itself. So this is the list of devices. As you can see, so these three are the simulators, and these are all the QPUs. So D-Wave 1 is available 24/7, but if you look at other ones, they are available only for a particular window. And you can click on that to get more information on that. So for each device, when you click on them, you get a bit more information, description of what the device is. Yeah, also link to the QPU providers to learn more about it. Availability, what time window they are available. So IonQ is available from 1 o'clock to 2 a.m. UTC, and what regions they are available in, and the cost. So we'll come to the cost in a bit. So here it's showing it's currently located in Maryland, USA, which is close to the US East 1 region. And if you, so it's got 11 qubits. This is Ion Trap 1. And with Ion Trap technology, they can connect any qubit to any qubit. So that's any to any connection. There's a fully connected graph. And a bit more on the calibration data. So as you can see, they are updated regularly. This was updated at 11 a.m. UTC, like 3-4 hours ago. And you get the details of the qubits and what their calibration data is. So this is for IonQ. If you want to look at maybe Rigetti. So this is the connectivity graph for Rigetti. So Rigetti is an 80 qubit quantum computer, but as you can see, not every qubit is connected to every other qubit. So it's so when you submit a circuit, what Rigetti do is they compile it in a such way that they convert the particular qubit you give and they map it to a particular qubit on the backend. So that's done by Rigetti, and you can see more statistics of each qubit and different calibration data here. Right, if we go back to devices, yeah, D-Wave is a annealing one, so this is slightly different. So here they are different technology. So this is called Pegasus and Chimera. It'll be covered tomorrow in great more detail. So I'll not go into that at all today. One thing I need to point out is this device ARN. So every resource within AWS, they get an identifier called ARN, it's Amazon resource name, and it's a long string that tells you what service it is, which region it is, and what type of it is, and each is a unique name. So this is what we will use in our programs to submit the jobs or tasks to the devices. So the device ARN is the key for using these simulators. So every simulator also has the device ARN, and that's what we use to submit the jobs. Notebooks we saw, so maybe I'll show. We quickly ran through earlier. So just want to show what else is possible. So you can select different notebook instance types. I think there was a question asked about why we would need this. We mentioned so there are GPU-enabled instances available as well if you need to use those local optimizations. If you need a larger storage, you can add additional storage. So we talked about IAM role. So you can customize this IAM role as well. So we went with easy option of create a new role. Everyone has a new role created, but you can create a role yourself, restricting it on what access the user is allowed, and then select that here as well. This is the encryption we talked about. If you want to encrypt all the data in your notebook, you can choose a custom key. This is what the KMS I mentioned for. So you can select a KMS key and assign that for the encryption. Networking part. So by default, when you create, the notebook is created in a service managed VPC. VPC is a virtual network which is created within AWS environment. It's a virtual private cloud. But if you have any organizational requirements for on the networking side, you can attach these notebooks to a particular VPC, especially if you're going to use access data from other resources. For example, if you're running an experiment, you need access from your other operational system. You can have this attached to a VPC, which has got access to the source system. So that's where the VPC part is useful. And the Git repository is, again, you can, if you have an internal repository, you can connect to that, and every time you spin up, that repository will be cloned automatically in the notebook instance. So this is just a quick rundown of what other options are possible. And the next we'll look at tasks. Tasks is once you start submitting the circuits, each circuit is a task. And so let's talk about what tasks and shorts and jobs are. I don't know if I have a deck for that, but we'll cover that now. The task is a single execution of a circuit. So it contains what the circuit information and also the device information and the number of shots to run. What is a shot? Shot is a single execution of circuit. Given quantum computing is probabilistic, so we normally run the same circuit multiple times to get a feel of what the results are. So it gives a probability distribution and to get a good confidence of the computing output. So the number of shots is key, and normally it's 100,000. We do that as to get a good feel and good confidence on your results. So that's a shot is a single execution, and a task is a single submission to a device or a simulator. The pricing for Braket is depending on for the QPU is depending on the number of tasks and number of shots. For each device, it's a different one. So if you go into pricing or if you look at the devices, you'll see those pricing. Jobs is something we'll cover tomorrow. So this is used for creating the classical and the computing job together, where you need to go around, run a quantum circuit, then do some classical calculation, and then go around that loop, should we say. This is useful. So instead of doing the classical computing locally on your laptop and then talking to AWS, to the QPU, and then coming back, what you can do is you can package them together and then submit it as a job. And Amazon Hybrid Jobs manages that whole execution for you and publishes the results periodically. So it all managed using Hybrid Jobs as a service. So that's a rundown of the console and how you look through that. Should we any questions so far? If not, we'll take a quick break and then come back and dive into the labs.
I'm just answering a few questions here on the chat, but nothing major, Jax.
Okay. I have my chat has frozen. Can you still hear me?
Yeah.
Okay.
I think we had a question here. Let me read it for you. Is it possible to provide a user-defined name for a task, or the only way to refer to it is with the system-defined task ID?
As far as I know, I don't think there's a way of defining a user-defined name for a task. It's the task ID. So what you can do within your programs is you retrieve a task ID and store it in a useful variable within your notebook or within your program, rather than, so it's not stored in AWS service as with a unique name.
Also, could you repeat the distinction between tasks and jobs?
Right. A task is a single submission of a circuit to a simulator or a device. A job is an overarching part where, so for example, we have not gone into those details. Maybe it'll be clearer tomorrow. Where when you run QML or some of these hybrid algorithms like QA-OA or VQB variation algorithms, where what you do is submit a task to a QPU. These circuits have some adjustable parameters. You run the circuit, and then based on the results, you adjust those parameters. So it's like machine learning. where you have to adjust the parameters and submit the task again, and then look at the results, adjust some more, and then submit it again. So when you have this continuous multiple runs of the tasks, a job is a way of managing that. So the classical part and the quantum part together as a package, you submit it and you provide a container instance and the instance size. So we, as a part of the Braket service, we spin up the classical compute part and manage that execution as a whole for you. It's like multiple times. You can keep it running for a few times. So instead of going back and forth between your local machine and Amazon cloud, you can do all that in a single environment. We'll go into a bit more details on jobs. Did that answer the question for now, or is there any more details needed? Perfect. Now the question: should we take a break for
Yeah,
10 minutes then? 5 minutes?
yes,
Should I say, or
let's
10
take
minutes?
a break. Yeah, I think 5 minutes would be sufficient. You are the boss, Jax. You say.
I don't mind. It's more just okay. Let's go for 5 minutes, and then we'll
Let's
back
go
in.
for 5 minutes. Yeah.
Yeah. I'm back one. Hopefully.
I was just pinging David separately and see if he can join us for the Kids part.
Still no.
All right, everyone, we're gonna go hands-on, so get ready.
Almost. We'll go through a few more slides, but this will hopefully be. So I'm hoping everyone is back. There's no way of seeing that, so but let's continue. So just want to, so for those who are completely new to quantum or very new, I just want to cover a few basic things before we jump into the notebooks. So one thing we see is, so the qubit is represented with 0 and 1 like a bit, but it's slightly different. So it can take positions like values that are in between 0 and 1. So that's the key nuance of a qubit. So it's represented as a block sphere. So this is more for us to visualize a qubit, and it's more for us to make sense of things. It works for a single qubit, then it very soon when we go beyond 2 qubits, it's really difficult to visualize all the interactions. Let's start with this for now. So it's represented in such a way that in a sphere, if the qubit is pointing towards the north pole, its value is 0. Right? That's one representation. And if it is pointing towards the south pole, its value is 1. So in classical world, it'll either be 0 or 1. That's the only two possible values. But a qubit can exist anywhere on the surface of the sphere. That's one way to think at it. So that is called superposition. So say it's pointing towards the x, it's kind of represented using this term. So it's what this is saying is it's halfway between 0 and 1. It's equal when you measure it. It's equally likely to be 0 or 1, but only one of them. So that's where the measurement comes in. So these quantum states are written in a form as a linear combination of 0 and 1. And each of these have a coefficient in front of them called amplitude. So this amplitude tells you what's the probability of that outcome when it's measured. So for example, when it's in qubit 0, A is 1 and B is 0. So that's why when you measure it, you always get 0. And that's the key thing. So when your computation is done and you measure the qubit, you'll either get 0 or 1. There's no way to observe the state in between. So that's the fundamental principle of quantum mechanics. So the act of observation collapses the quantum state, and you observe either 0 or 1. The 0 and 1 are arbitrary. So as we saw in the block sphere, it's along the z-axis. If you go back, so along the z-axis is where we have chosen the zeros. That's what all our gate operations are based on, this kind of imagery in mind. And when we look at the gates in a second, you'll know what I mean. So how do you measure the probability based on this? So the amplitude squared gives you the probability of that outcome. And every quantum state, you have to represent that such that when you square all the amplitudes and add them, you should get 1. So that's the normalization part. So if you look at this example here, both A and B are 1 over root 2. And if you square that, both are half. So that's why this is called an superposition, where it's an equal probability of getting 0 or 1. So think of it like literally a coin. When you flip, it's an equal probability of getting 0 and 1 if it is a fair coin. Next is quantum gates. So quantum gates are they allow us to manipulate the state of a qubit. Mathematically, they are represented as a matrix. So it's a 2 by 2 matrix. You can imagine it as a rotation. So for example, we'll take one gate. There are poly X gate, or it's also called a NOT gate, equivalent to the classical NOT gate. Anyone wants to guess what happens when I apply X gate or the NOT gate if the value of A is 0, the qubit is 0. Once you apply next gate, any guesses on what the output will be? You can put it in chat. Yes, right. Yeah, it's going to be 1. And when it is 1, if it is starting as a 1, when you apply next gate, it'll be 0. So one way to imagine this, or that's what it is. The X gate is a rotation along the x-axis, around the x-axis, by 180 degrees. That's what the X gate is. And you can imagine based on that, there's a Z gate and a Y gate, and correspondingly they are rotated along those axes. So if we get a Z gate, it's rotated along the Z axis. Same thing with Y along the Y axis. So those are gates. There's another important gate called the Hadamard gate. So we saw this expression earlier, which is an equal superposition of 0 and 1. So the qubit is pointing towards the x-axis from 0. So that the gate that allows you to take from 0 to that positive x-axis is called the Hadamard gate. So the Hadamard gate is an important one. It puts a qubit in a superposition, in a equally 50-50 superposition. That's the key part. And if you have a qubit in state 1 and apply the Hadamard gate, if you can imagine, it'll take it to the minus x-axis, so literally behind the positive x-axis we saw earlier. So one of the key things about quantum computing and these gates are they're all reversible. So if you start from this state and apply Hadamard gate, you will get 0 as well. And same here. So if you start from a -1 state, you'll get back to 1. Now let's jump into multiple qubits. So one of the gates from the classical world is an XOR gate. You can, so there, it's in the truth table. If you look at it, it'll be the output will be 1 if only both the inputs are 1. So that can be achieved in a similar way using what is called a control NOT gate in the quantum computing. So this is how it's represented. So the dot is called the control qubit, and this is the NOT gate, the X gate we saw earlier. So when they're linked, so what happens is when A is 1, only then the B state changes from 0 to 1. So for example, if both are 0, what will be the output here? Guesses from the chat, please. Oops, I jumped. Correct. And the next one, I'm clicking before I allow you to answer, but yeah, the next one also, the B doesn't change because the A is 0. Right? What happens when the input is changed? The control qubit is 1 then. So what happens to the output here? Right, that's 1, 1, and the last one is 1, 0. So basically, this changes if both A and B are different, then the output is 1. If both are same, the output is 0. So that's one way to look at it. So that's the XOR gate, the equivalent of an XOR gate. Right. So we have seen a 2-qubit gate, but how do you represent the state of multiple qubits? So it's similar to how we represent a single qubit. It's very similar. So say, for example, you apply Hadamard gate to 2 qubits. What happens is, so this represents state of each qubit. So if you have 2 qubits, there are 4 possible states: 0, 0, 0, 1, 1, 0, and 1, 1. So this is a generic representation of a 2 qubit state. So what this is saying is, so it can be when you measure it, it can be in one of these 4 possible states, and A, B, C, and D are the amplitudes. So if you square all of them together, they need to add to 1. That's an example. If you have 2 Hadamard gates, there's an equal superposition, or equal possibility of all 4 outputs, which you can observe. So the value of A, B, C, and D is half. So when you square them, each is quarter. So this is one way to represent multiple qubits. Okay, there we have seen superposition and how we can do multiple qubits. But another key concept is called entanglement. This is one way to see is it's a coordinated action at a distance, or as Einstein called it, spooky action at a distance. How can you achieve this? Is what we will start coding up in a bit. So let's say we have a Hadamard gate on qubit 1. Yeah, then so now this is in superposition. And then you apply a CNOT gate to qubit 2. What happens? Can you any guess on what the output will look like? Yeah, that's an answer in the chat. So whenever this is 0, nothing will happen, right? So this will stay 0. But whenever the output of the Hadamard gate is whenever it's 1, this will get changed to 1 as well. So you'll never see 1, 0 or 0. So you'll always see these are only 2 states that are possible to observe. So that multi-qubit state we saw, the terms 1, 0 and 0, 1, 0, sorry, 1, 0 and 0, 1 are no longer possible. So this is the state vector of as output of this particular circuit. And so this is something you will build using Braket in the notebook. Yes, that's I see the answer as well. Yes, perfect. It's called a GHZ circuit. So this is chaining multiple qubits, and you get the same result. Because so once this is 1, this changes this to 1. If this is 1, then that feeds into the next qubit, and that also changes to 1. So when everything starts from 0, the output will be, so this is called maximally entangled state. So that every qubit is entangled. So you'll, in a noise-free environment, you'll observe all zeros or all ones. Those are the 2 observations. So this is all wanted to cover. Let's now jump into the notebook. Go back into notebooks and click on your own name. That should open up a notebook. So here, once you're there, you should see a clone of our examples repository with all the example notebooks. For today, what we're going to, I'm going to, you can explore those as well, but we are going to upload a notebook in the Chime chat. You can download that and start using that for now. Or do we have a link one? I can drop it here, right? There's nothing.
What is that again, Jax?
the example notebook, you don't have a link to share, right? I can drop it in Chime chat window, right?
Yeah, you can attach it actually.
Yeah, I've attached it to the chat. Yeah. Should have all that. So if you can download that from Chime, and then you should be able to just drag and drop here. No, not here. Sorry.
I was optimistic.
I, I thought you could do it, but maybe not. Yeah, you have to drop it in this window here and then click upload.
I learned something today.
It has to be in this part if you drop, or you can go and upload, click this upload button and then upload as well. Same thing.
You make your screen a bit bigger, Jax.
Oops, too big.
That's great, thank you.
I'll open the notebook and make that a little bit bigger so that way it's. So and if you can load it into this notebook instance, open this notebook, we'll continue from there.
If anyone is not seeing what Jax is showing in the screen right now, could you please +1 in the chat?
If you want to make it a little bit bigger, I can do it as well. That's. Yeah, there you go.
That's perfect. Seems like everyone was able to upload the notebook.
Okay, so I hope you have all downloaded. If you still need Sime or anything, Q+1. If not, we'll continue in 10 seconds. Right. So initially, we have a couple of imports. So this is for plotting the results. And we're importing a circuit module from Braket and also local simulator from devices. That's the initial part. And other thing is, so if you're downloading your own notebooks, so make sure if you're creating a new notebook, you have to pick a kernel. These managed notebooks come with just one kernel called Conda Braket, so it's making that easy. So this comes with all the libraries pre-installed with the latest version, depending on when you spun up the notebook. So to build a circuit, so you can chain these different gates. So you start creating a circuit, so that instantiates an empty circuit. Then you keep adding gates. So you don't need to define the total number of qubits up front. You can start defining, so you can start giving these numbers that will start adding qubits. So here what you have done is added Hadamard gate. H is for the Hadamard gate. And we're saying add it to qubit 0. So here we start numbering the qubits from 0. Unlike the picture, it says 1, but yeah, that's we start from 0 for the numbering. And then for the CNOT gate, you have to specify which qubit is the control and which qubit is the target. I'll switch off video so the bigger you get a bigger screen. I should have done that earlier as well. So you can also, as the command says here, you don't have to specify control equal target. The default convention is the first qubit you give is the control, and the second one you give is the target. That's the default convention. So you can simplify to C0, 0, 1 as well. And if you want to visualize the circuit you're building, you can run the print and the circuit name as well. So that will print an ASCII version of the circuit, and it shows different steps. So we talked about just X gate and Hadamard gate in a single qubit gate. And as I mentioned, because gates are a rotation of a qubit within the block sphere, you can technically build any kind of rotation with arbitrary angles with random rotations. So there are many gates. You can explore all the supported gates in the link here. Hopefully you can see this. So this lists all the supported gates by the simulators, and also so that gives you the full gate set for the circuits. And there are some gates that are supported by some QPUs and others. So there's something to look into when we are going into advanced topics. Then this explains different gates and what inputs are expected for those. Right, now we have built the circuit. Let's submit this. So how do you define? You define a device. So the local simulator is what we imported earlier from the devices. You set that up, and then you use the run method on the device and submit the circuit. So this is doing multiple things here. So it's using the device, the local simulator, to run the build circuit, which we set up here. And the number of shots, that's how many times it's going to run these. And then after it is run it, because it's a local simulator, it's expected to be quick. We are also updating the results after the run and storing that results in the result variable. So it's chained multiple things in one go. You can do one at a time as well. And then once you have the result object has multiple things. What we're interested is in the measurement counts. So when it ran 100 times, how many times did it get 0? How many times did it get it 1? What were the results of that? And then you can print that. So this is a simple hello world example of a build circuit using a build circuit. So when I run this, as you can see, based on the entanglement, we got 0, 0, 57 times and 1, 1, 43 times. You may get different results, but it should be close to 50-50. So I'll run it again, and now 51-49. I don't think it can get any closer than that. I've never seen 50-50 ever. Just a question. So why do we see these differences? Why is it not 50 and 50? Anyone wants to answer it in the chat window? Yeah, the common misconception is it's because of noise. It's not. It's probability. So even if you run it one time, it'll be either 0, 0 or 1, 1. So that is technically possible. Like if you run it 10 times, you might get all 10s as zeros. It's possible. We very rarely see, but it's still a possibility, not probability. Oh, wow. I've never seen 50-50. It looks like few people have got 50-50. That's, yeah. So, um, so yeah, we're not going to cover, maybe we can cover noise today as well, depending on the time. It depends on what we do. So if there was noise, say this, we run this on a noisy, we will see. Do you want to guess what the outputs will be then? So if this is not because of noise, what would you see as noise? Yeah, you will see some results for 1, 0 or 0, 1. Perfect. This is a bit more way up to visualize the results. So I'll pause here. I'll let you play around a bit, maybe a few minutes if you're already not doing it. And then we'll jump into JHC circuits. It's similar to this, but a bit more larger, more qubits. And if you have any questions, please put them in the chat window as we go along, or you can unmute and talk as well.
Right. I will answer some of the questions. So go ahead, Jax.
I was answering on mute until now.
Go for it.
Sorry. I was saying the account access will be available for 3 days until Sunday morning European time. So today, tomorrow, and Saturday, you can use that. And the queue, the notebook, you can click this upload button and select from your local machine and upload, or drag and drop it to this area here. I've not seen all the questions. One, did I miss any questions?
Maybe you can do the upload piece and just clicking on
Yeah.
the upload button so they can see it.
Yeah. So if I
I
click
can't get to
upload, go to downloads and select, I can't find it. There you go. It's a different one, but yeah. And then click upload.
Yeah, for the other questions, the other question was, so Braket circuit has the same structure of Qiskit circuit. It is similar in the sense that you append gates to an initial circuit. So in that way, Qiskit and Braket work the same way. Yeah.
Yeah, right.
And then I have here, is there a measurement gate on the Braket SDK, like Qiskit measure all instruction? No, the Braket SDK do not support measurement gates as per today. It's a thing that we have started to hear more and more from customers. It might be implemented in the future.
Currently, by default, all the gates are measured. All the gates, sorry, all the qubits are measured in the results. Right. If you want, you can play around a bit more, and then we can jump into the next part. Have a change around, like define your own circuits, add other random gates if you want, and then observe the results while you're at it.
Someone was playing with 4 qubits. That's great.
So let's go beyond 2 qubits now then. So now we are importing a bit more. So we are using AWS device as well now, so we can start submitting to simulators and qubits. So we have, because this is Python based, you can build circuits using routines, loops as well. So this is showing that. So here we are building a GHZ circuit. It's a helper function for creating any number of qubits. Sorry. So here we are instantiating a circuit, adding a Hadamard gate, and then adding CNOT gates for rest of the qubits. So that's depending on, so the input is the number of qubits. So this is how you define it. So you say like n qubits 5, and then call the circuit, and then that returns the circuit with the structure. So now we can see the results. So it'll help if I run all these, right? So run. So that I set up everything, now I should see a 5 qubit. So this is a better graphical version of it, but this is what you see here. So now we want to run this circuit. So I'll let you explore here. If you want to suggest what I should be typing here, I'll do that. We can keep this interactive. So how do I define a device to be set as a local simulator? any suggestions on the chat, please? Yeah, that's right. Daria has mentioned. What happened here? I lost my top window. It's back now. Yeah. And I want to run the circuit. I want to run the GHC circuit on this device. So how do I do that here? Yeah, Christine has given right. Joel and Christine have given that. So I'm just going to use what they given here. Right, that's the answer I got in the chat, and that's correct. So here, so the key thing to change is what circuit you are submitting from the previous one. You can do that, but if you want to run it and take it differently, so you can also, I think there's the next example is going like that, but I just want to show you a variance here. You can, that'll work as well. Definitely, that's what we did earlier. Also, what you can do is, because this is a task, you can say task or whatever variable name you want and just run that and then get the result later in like result equal task. It lets you explore what else is available in the task apart from the results. So that's something that could be useful. So now the result is stored in the result, same as like this, but we have to split that now. Maybe I can add a cell before here. And maybe print task to just show you what is there in the task object, so you can explore those as well. So that's the task ID of what was submitted. So that's it is again, this is just a local task, but still it generates an ID. The SDK generates an ID to keep track of that. So now you can get the task results. Sorry, and how do from the result? Now how do I get the measurement shots? Yeah, exactly same as before. In I'm going to pass this. Look at the object here. That's giving the results of the counts from that, and you can plot the results. You can just use the same graph we use. We don't, yeah, that's that plots. So as you can see, the same. Right now, if I change the number of qubits to a very large number, like 2020 or something like that, it takes a long time to run on the local machines. That's where the managed simulators come in. Sorry, I've scrolled probably too much. I lost track of where I was. There we are. So now we will start using managed simulators. So here we have defined the state vector simulator, SV1. So this is the ARN we talked about. So you can get this ARN from the Braket console, from the devices and SV1. So that's where the ARNs are. And if you look at other example notebooks, you can get that programmatically as well. So that's for you to explore when you have some time later. Right, so I'm setting now device to SV1, and now I'm going to do, that's already, so it says 15 and we have 20 here. So we're going to define a 20 qubit circuit, and it's the same flow. So as you can see, the only difference is the device. Everything else exactly the same as you run in local simulator. And you can run this on. Right, so we have now done this part, and so as you can see, for this 20 qubits, we have got 504 and 496. It'll be interesting if someone gets 500, 500. Please let us know if you get that, and then you can definitely go and buy a lottery ticket. So I'll wait for you to maybe run those things, and then we can look at what else is available to get a bit more on it. 501, 499. That's the winner so far. So now we have submitted the tasks. So let's run this and get the task ID for now. So that's the task ID. Earlier you saw just a random hash. Now you see a full ARN of the task. Now because we have submitted it to AWS Managed Service, now you can go back here and click on tasks. So these are different tasks we have submitted. I think all 5 of us are using here because we submitted at very similar time, have submitted a task here. These are each from a different notebook, but on the same device, and these are the tasks. Right. We have looked at the task and how we got these results, but how is the SDK getting out these results and how is it working when you submit it to the device? So let's pick one task here. If you click on a task, you see the task ARN where it was submitted, and there's a link for S3. So S3 is our storage service. So this is an object storage, and you can click on it to open that console itself. And so what happens with the Braket SDK now is you don't have to specify S3 bucket as a mandatory. It used to be mandatory when the SDK was launched initially, and now it's not mandatory. So if you don't specify an S3, what it does is it creates a bucket with Amazon Braket, the region name, and the account ID as the default bucket, and stores the results of the tasks in a folder called tasks and the task ID. So I don't know which one I click, 90, that one. So here, there's a file called results.json is stored. So this is where all the results are stored. So you can click that and download it and open it. Right. So this is what is stored in the results. Those measurements you saw for those, so each measurement is listed here as a list of lists, and it shows how many qubits were measured. So 0 to 19, so 20 qubits. And there's also metadata related to the task, different schemas used, and additional metadata. This depends on whether you're using a simulator or a QPU, and this varies depending on where you're running your circuit on. And also like when it was created, how long it took. So it has all those, a second or so. So this is how the results are stored, and the SDK uses this data to fetch the results and formulate it to be consumable within the notebook here. So we got the task ID, and you can also get, so we solved the results file. So the similar things, you can get that from here. So we are getting value of number of qubits in that circuit, and also print that. So we can try those. So we are printing both task ID and the number of qubits. Yeah, that's getting that from that. So the data from the results.json file is used by the SDK to retrieve multiple values from the task that you are submitted. So apart from the measurement counts, you can measure other things as well. You can get the expectation values in for different observables. So the default is the Z observable, but you can look at other supported result types here as well. So you can, maybe I'll show that in a second. So you can get the amplitude, expectation values, probability, density metrics, the whole state vectors, and the variance. But not everything is supported everywhere. So local simulator supports all of them, but there's a varying level of support for other device result types depending on the device. Going back to the notebook. So now we'll try to submit it in TN1. So this is, you can continue and do it yourself. So I'll wait here. So get the ARN of a TN1 device, add it here, and run this circuit in TN1. And then you can get those results and you can look at the results. I'll wait for you to do it yourself and then I'll run it here. Yeah, that's Marciano has put in the ARN of TN1. That's correct. You can put that and run it. The TN1 here. So now if I go to tasks and see already couple in my group who are sharing my account have run, already 2 of them have run it. I'll now run as well. And it's the same circuit with 20. And as you might have already noticed, this takes slightly longer than SV1. It all depends on, because it has multiple phases, it has to do a rehearsal phase and then contract it. But TN1 is more suitable if you have a very large sparse circuit, which is not possible to run on SV1. Mhm. So many of us are running on TN1 simultaneously. We have them queued. So while that is running, you can't do much in the notebook. So if you want to explore the results file, go ahead, because there's one of the tasks here to compare once for those for whom it have just already completed. Look at the results file and see how the SV1 and TN1 simulations compare from a time-wise. Are they running? Yeah, some are getting completed. So, yeah, one team completed this. Yeah, minus completed. Yeah, so what if yours is completed, please go ahead and try to see the completion times, the execution times, I mean. And I'll let you play around for a bit, then we'll jump into running it on actual QPUs. One thing to mind, if you're already submitting tasks on QPUs, go back to the devices and see which one is online now. So as you can see, the only one that's online is IonQ. The others are all offline. So if you submit on those, you will not see them. So this one is going to be available in 45 minutes, Rigetti. Oxford Quantum Circuit is not available until tomorrow morning.
Just to be precise of the on the wording, there's a difference between unavailability and offline. So the ones that you see with the clock are unavailable, and only one device is offline at the moment.
Yes. So this will, there's no, sorry. I was going to repeat what you said. I'll keep quiet.
No, please don't. We will get to the QPUs in just 1 second, guys. Just be patient. We will explain everything you need to know about how to submit your jobs, your tasks to them. Are you talking by any chance, Jax?
No.
Okay. I thought that you probably went on mute again.
Keep doing that. At the moment, because there's only IonQ available. I don't know if you want to flood IonQ with lots of tasks. As a Christian is asking a question about what happens when the device is not available, they go into the queue. If it's offline, it doesn't go into the queue. Am I right, Juan? You can't submit a
That is
task to a device
correct.
that's
If the
offline.
device is online but busy, or if the device is not available in the time window, it will go to the queue. If the device is offline, the task will fail.
Oh, sorry, you already answered in the chat. I'm just catching up.
You are not able to see the queue, Laxmitar. You know that you are in the queue, but we don't have a method to tell you are in position number 3 or number 20 or this is the estimated wait time. That's something that is not possible to do at the moment. Marciano, you just need to check probably that you are in the right region. If you don't see your task, that could be the reason. SV1 is defined by default in a different region where the QPUs are, for example.
All right. Should we try submitting a task to IonQ now? If you want some more time, we can. If you're ready to go to QPUs, give a +1. We'll then proceed. Just if we get enough +1s, we'll proceed.
Excellent.
This same as before. So pick a QPU. Currently, it's just IonQ that's online. What you can do is if you start early in the morning tomorrow, you can use OQC or Rigetti in a bit. I think last time when we ran this, it was just in time for Rigetti coming online. Sorry. Go and get the ARN of the device that's online, so which is IonQ, and run it. So here we can see the difference. We are not getting the results. If you put dot result here, this particular line will wait until the results are back, and that can be a long time depending on where we are. So what you're going, so that's why it's constructed slightly differently, because we are just getting the task like we did in an example earlier. Just getting the task, and then we have a task ID, then we can monitor the task and get the result only after it is completed. Right, now it's created, it's queued, it's currently in the state created. Now you can run these and to see what it is. It's currently created. Okay, keep running these to find out what it keeps. Now it's queued. If you go back to the tasks, you should see a few queued ones. So this can take some time depending on where I am and when you all hit it. So we should start seeing results in a bit. While that's going on, yeah. So this one, once it's completed, you can get a bit more details on the shorts, the device ARN, and it's a similar thing, but it's only when it's completed. Until then, it'll just go around. Sorry, it'll just wait. So this is how you recover a task based on the task ID, and then treat it as if you are working with the task now. So all this does is looks at the result file and then gets you the results back. So the other two blocks are for the tasks. I'm just seeing what else is there. So yeah, that's all we had lined up for today, and we have a bit more time. Let's play around for a bit, and then Juan, do you want to plan
Yeah.
something else as well? Or
I just want maybe just talk a little bit about some of the questions we are getting into the asynchronous nature of this part. Do you mind to go to the devices section, Jax?
yeah,
Yeah.
yeah,
So as you can see, guys, so we execute this code in a slightly different way, in which you can just basically get the state rather than lock the cell until the task has finished. For the simulators, it's easy to do it that way because they respond immediately. But as you can see here, IonQ is available right now, but usually we're seeing queues in IonQ of around half an hour, more or less, to execute. This is not bound to AWS, but the time that the vendor has on processing customers' queues. So for everything that you launch in IonQ, maybe in the next 30 minutes or so, you will see your results coming back, and you will be able to execute the rest of the notebook and see those results. As for Rigetti, as you can see there, in 37 minutes, same as Xanadu, is going to be available. So that means that just by the time that the workshop is finished, those things are going to be ready for you to use. And Rigetti's queues are much faster. They usually are processed in a much shorter time, sometimes almost immediately, like a simulator. So what I would recommend you to do, if you are still around and have the energy, that you keep practicing with this, because the environment is not going to close. So you can use the Rigetti ARN and launch your task and get your results almost immediately. One last thing to notice for another question that I just replied there in the chat is that you don't need to be refreshing your window all the time to try to see your results or what's happening. If you want to explore, and maybe tomorrow we can cover it if you want, Event Bridge, with that service you can basically configure email or even an SMS to be sent to your phone completely free when the task has completed. It just takes a few steps, but maybe it's an interesting exercise for you to do and explore. You need to create a notification in our SNS service. And then in Event Bridge, you can say, whenever my Amazon Braket task changes its state, send me a message, this email address or this phone. And that way you don't need to keep monitoring all the time. So that's also a possibility. All right, and with that, I'm maybe gonna cover the rest of the questions. Can be rejoined the environment later? Yes. I sent you the guys the. You go ahead, Jax. You can answer that
I
one.
can show that here. So if you copy this login link as well, so you can use the URL from there to directly come in, or if you give the same email address, you'll get into the same environment again. You just need the code, the event code, which we gave earlier. We'll share that. I think Juan has shared a handout document.
Yeah, I'll put it here again one more time. You just follow those instructions if you don't have the link that Jax just mentioned, and you will get in again. Let me read this question from Daria. Any difference between this? This is a task versus first one task ARN, the other one task ID. Is how you use it. So the ARN it will be made by the ID, I believe. Oh no, it's
Yeah,
not. It's
ARN
interesting.
has. No,
Go ahead, Jax. You get that one.
ARN is the ID. So F85 starts. It's the same thing.
The same thing, right?
Or
It's
yeah,
just
it's the same thing.
the ARN
But
gives the whole path that helps
yeah,
you to find within AWS which service specifically is using it. It's like AWS wide definition of that specific task. Maybe you want to complete the answer, Jax.
so the SDK uses the ID to keep it simple, but you can give both. So if you just give that as well, it work. But it's the ARN. So it's here you can see ARN equal to task ID. It's the same thing. So for depending on where it is, so I would recommend using the whole ARN.
Perfect. Okay, we have a bunch of questions here. Let me keep going. I was able to use Qiskit's Braket provider locally, but I had a problem with the notebook at AWS. Do I need to reinstall it? Not sure I get it. If you install the Qiskit Braket provider is to be installed locally in your Qiskit environment. So if you're a Qiskit user and you install that provider, then you will be able to use AWS Braket endpoints. If you install the Qiskit Braket provider in a Jupyter notebook of Braket, you have those libraries there to experiment, but you are really not using it on the right way. So the provider is for the Qiskit environment. Gabriel, one doubt. I've only run once on IonQ and I see 2 tasks in the task list. Is this because the account is shared with another student, right? That's exactly right, Gabriel. 5 of you are sharing one account. So you will start to see a lot of tasks when people start playing with these devices. So it's good to grab the ARN ID or the task ID to find yours.
Yeah. So as you can see in so there are 3 tasks submitted to IonQ. Only one of it is mine. Other 2 are 2 of my fellow account sharers.
That's right. Perminer is just adding more color in the ways that you can configure your environment. I'm going to paste once again that link over there. If you want to do that, you can definitely install everything locally. Just bear in mind that after 24 hours or 48 hours, everything is going to disappear. So if you have something valuable these days, just make sure you save it because the accounts will be deleted. all the steps from the Conda and Jupyter environment, everything will be explained on that link. You want to start from scratch. So Braket acts as a backend for Qiskit via the Braket provider. That's right. When you install these libraries, you are allowed to add new endpoints to the ones that IBM offers to their customers. So you are able to use the Braket endpoints. Excellent. Okay. Yeah, it's a pity we have half an hour. I could have prepared something on noise. We can keep these people entertained for a bit longer. I thought it will take longer, but since I didn't prepare my slides and my exercises, we are gonna
While we are
stop
waiting,
here.
maybe you can open up a new notebook if you want a bit of a challenge. It's not if you're so you can we saw entanglement like 0, 0 and 1, 1. Can you think of building a circuit where you will get results as always like opposite? So it will be either 1, 0 and 0, 1 and never same. That's also possible by building a circuit. Maybe if you want to experiment and give an example here, that will be something to play around. So the output we want is 50-50 of 0, 1 and 1, 0. Something like that. Put it in the chat window. That's what we are looking for.
To answer Nicolas' question, all I can say is that we keep looking for people. He's asking for careers at Amazon related to quantum computing. We have a growing team that is expanding really fast. We are always looking for software developers who have an experience in quantum computing or a background in quantum physics. So with the link that I provided later, you will find what is available at the moment. It doesn't matter if you are an intern looking for an internship or a full-time job as a changing from the industry, from the academy to the industry. You can apply there, and yeah, it's basically the process. The team is made of applied scientists and software developers, and it's a very diverse background on its composition. So I can say it's a great place to work with, and it's a very helpful and cooperative team. We always help each other and learn from each other. So it's exciting to work in quantum. Probably you know that already because you are all here trying to learn it, right?
Just looking if David is back. They have not come back, are they?
I dropped an email, but probably he didn't get it. We can even try tomorrow again.
Yeah. So while if you're waiting, let's just double check it has not completed yet. No, it will complete eventually. So other things to explore is if you go into Braket examples, there are a couple of things like getting started is almost what we have done, and on that there's a deep dive into anatomy of quantum circuit that goes into depth of like different aspects of the options while building a circuit. So and the other one is Braket features. That's more specifically on. So those two will be interesting to explore when you have time. So different ways of doing it. It's more deep dive into TN1, and also open chasm way of submitting circuits, where you can use the open standards of building a circuits across here. So there are a few things you can explore. We have time now, or you have access to the labs after this as well. tomorrow we will be covering hybrid jobs, maybe a bit into these two with using hybrid jobs and quantum annealing.
Yeah, more things I wanted to share. Those notebooks actually be our beta testers for us, if you don't mind. Go into all the notebooks when you have time from now until tomorrow and run them and see if there is something odd or something that you don't understand or it doesn't work. And let us know, because we are always improving those notebooks. And sometimes as we release new versions and new features, some things break, right? So play with that, and I would like to see a lot of usage in your accounts when I look again tomorrow. I encourage you to do that. One thing I wanted to ask you to do, Jax, is if you don't mind to download one of the notebooks as a notebook, sorry, as a Jupyter notebook, because one of our participants is having problems downloading the notebook.
Any one of them?
Any one of them, anyone will do,
I'll go for the noise one.
just to show how it's done.
File,
You mind to make it a bit
download
bigger?
as. Yeah. So once you open the notebook, you can do file download as. It's a notebook here. That's one way. Or if you want a proper IDE-like experience as well, that's another option. If you go and click this Open Jupyter Lab interface, it gives you the access to Jupyter Labs interface, which is a bit more, I was going to say better. It depends on how you want to look at it. It's a proper IDE experience, and you can, same thing with that. So you can go and right click and, oh, you can't right click and download here. The same thing as file, same here. Export, save and export notebook as. You still need to open it, sorry. That was not a notebook, that's why.
That was a folder, right?
That was a folder, yeah. Yeah, you can click, right click and download. I thought I was losing my mind. I thought you could right click and download. Where did it go?
That's how it's done. Slawomir, that was for you. So Gabriel, yeah, your question about the differences on the duration between the tensor network and the state vector simulators. The state vector simulator is straightforward, gives you all the results that you pass with the full wave function as Jax was explaining before. The tensor network, however, goes through two phases before giving you the results. First, it does a rehearsal phase or rehearse phase, and then it does contraction before showing the results. Instead of giving you all possible results, not in this case that we run today because you use a simple example, but when you have a graph type of problem, this tensor network simulator will try to traverse that graph in the most optimal possible way, and it will discard all the possibilities that are not feasible. So for that reason, it takes more time to evaluate all the possible matrix multiplications that happen behind the scenes, and the execution will be longer. So that was why.
And if you want to deep dive, did I say no? The one we were looking at is, you can look into the TN1 specific ones within Braket features. Yeah, you can look at this, which goes into a bit more details on how it works and yeah, that comparison of different tasks on different simulators as well.
Oh, I'm having a big backlog now of questions here. I love it. Let me see. Also, do you have any educational research packages so that we can keep working on these machines? Interested for opportunities for you as universities and students. This is a very interesting question, Nikos. We've been talking about this and how to make it easier for customers to use the platform. I'm going to give you the contact details of one of my colleagues. Why don't you drop me an email? That would be the best way. Drop me an email, because I'm based in the US as well. I put it just there, and we can keep the conversation going. Let me see. Can someone not from the available regions set up their account in any of those regions? The closest one, maybe. You are talking to the expert here. We have Jax in the call, who was the first person that cracked that nut when we got that question. Let me find the blog for you.
And if this is related to setting up AWS account itself, the account itself is not region specific. When you create an account, you have access to all regions. And so you can live in any country and access regions from any other country as well.
If that was a question, that's the answer. Yeah. I put here the link on how to configure a cross-region configuration where you don't have Braket in your current region, but you still want to access to Braket in a remote region where you don't have initially full access. Let me see. How to declare a 2-bit circuit. You can use the library, the function that was defined, the GHC function that we use today in our notebook, and set up the number of qubits to 2, and that will declare a 2-qubit circuit.
That will declare a 2-qubit GHC circuit. But unlike Qiskit, you don't have to declare the number of qubits before when you define. So as you add gates, depending on the qubit number, it will add qubits as needed. You don't need to declare beforehand. There's a question about
Marciano.
DM1. Yeah, Marciano. Go ahead.
Yeah, I was about to answer that one. So why is not? Well, we like to separate things that way. So the state vector is a general purpose one. The tensor network is based on graph type of problems, and density metric simulator is a state vector simulator, really. It works like the other one. The only difference is that I have the extra modules or the extra methods for you to add initialization noise, readout noise, depolarization, dephasing, bit flip, whatever you like. We think it was better to split it in different simulators, but no other specific reason. And remember that as well, the local simulator that is totally for free also comes with a density matrix module, so you can simulate noise completely for free without even having an AWS account by using the local simulator. Okay, I think we want to take some. Jax, do you see anything that I missed?
I didn't. That was the last question I saw. I didn't see anything else. Slawomir is going to try from a different browser to download. So I didn't see any other questions outstanding. If we
Perfect.
have missed any questions, please ask again so we get to see it. If you have missed any questions, please.
Right. It's great to have all these questions. I see that for the last hour, we maybe lost 2 or 3 people only. So that means that you guys are engaged and are there, or just forgot that the screen is running and went to do something else, which could be the case as well. But overall, I love the engagement. We have a survey, but I'm not going to give it to you until tomorrow. Because I want you to provide the whole experience workshop. And tomorrow, Jax is going to be also talking about hybrid algorithms and how we mix classical resources with quantum resources in order to run optimization problems and variational algorithms. We will explain all that, how to do that in Braket. And then we will bring another speaker who is an expert in annealing, and he's going to cover D-Wave, and he's going to explain to you the topologies of a quantum annealer, why a quantum annealer, and how it's different from a gate-based QPU, how to use them in Braket, and of course you will have access to the environment where you will be able to do exercises and play with these devices. So we have a lot of interesting stuff going on tomorrow. I will really appreciate if you can make the effort to join us, because at the end of the day, I will give you this survey, and we would love to get your feedback on your overall experience. I think we have more questions here. I missed the part on how to change the initial states of the qubits, so I added X gate to both bits to get, and that's the result there. So yeah, if you want to initialize a qubit to a value that is not 0, the only way to do it, at least in Amazon Braket, is to add an X gate, and that will flip the qubit to 1, and then you run your circuit. When you are running a QPU, you are by nature introducing some noise or already is different than the initialization. It's not exactly the same thing, but it's the only way it can be done in Braket.
It's a question from James on the getting S3 bucket from the task ARN. So if you're using the console, James, you can click on the task ID and you have the S3 results here. And because when you submit the task, you can give different bucket names. So if you're trying to use it from the SDK, I don't think SDK gives the S3 location directly, but you can use CLIs to get that information. You can use get quantum tasks, and that will give you the S3 location. So let me maybe try that. So if you launch a new terminal from your notebook, whichever interface you have, you give this bracket get quantum tasks. If I can type. Your filter, yeah.
James already got it, but we will explain it anyway.
The CLI also, you'll get all the task ID, and so that's the task ID, and then you'll get output S3 bucket under directory as well.
Laxmidar says that need help with this. Too difficult to debug like this. Oh, you said X. Oh, that was an easy one. In Amazon Braket, the X gate. Oh, my mind blanked suddenly. How do you call X in Braket?
Not an X as well. Can do an X. No, capital X.
Should be capital X, right?
So we saw here. So no, it's a small X. Well,
oh, so then it's correct.
X. Yeah, it's correct. But you are
Paramar gate in qubit 0 and an X gate in qubit 1. That's a bit of an odd circuit, but you can do it.
Okay, Darius answer works. You strictly don't need the X on 0, so you can just do X on the 1 qubit and you still get the same results.
Right.
So I'll show you here. Maybe we have given enough time. Maybe we'll do that last circuit here.
Yep.
So
that's correct, Joao. While Jax is looking for that. Oh, sorry, you're there already. Go ahead.
Yeah. So if you add X1 here, so that should add it. Yeah, this should give you the right results of what we were looking for. So that gives 0, 1, 1, 0. So what we're doing is changing this to 1 initial value. So that then, so whenever this is 1, this gets to 0. So it's swapping. So this is one example of how you can get. So I think in Daria, he added an X gate here as well. That also works because this is still putting in superposition. Even if you start from 0 or 1, it still gets to an equal superposition.
Right. Joao, you are right. The S3 bucket link will show up results are available when you, well, actually it's not technically true, but if you go to the graphical interface, you will see that there is only a dash there while the circuit is running. And when it finishes, it will populate automatically the S3 link for you to click. That's exactly what Jax is showing there. Rafael wanted to know how to get to the actual CLI using Jupyter notebooks.
So if you're in the lab environment, you can go File, New Terminal. But I don't know how you go back to the world interface, but I'll click the interface again.
Let's open it again, maybe.
If I open it again, so I should go to the normal one. So from here, you can go New Terminal. Or from within a notebook, if you already have a notebook open, you can run using an exclamation. So you can do like exclamation AWS. Braket. Maybe I'll try.
Right, that's a shortcut that you can use. Put in the exclamation mark that will execute CLI-like commands.
Yeah, so here I need to provide the task here, and so this is for the task that's running on IonQ. It's queued. I'm going to try that to see what happens, what we get for that task. So this is a CLI command. Get that same results. So in the GUI, it doesn't show the S3, but here you can see when you run it here, you can see where the S3 will end up, the bucket name and the output directory, even for the queued ones. So we don't show in the GUI because that is the link for the results file directly, not just the location. And the results file doesn't exist yet. So that's why there's no link there.
Thank you, Cesar. All right, so I think this is it. We have 10 minutes left. We'll give you that time to play with the environment. You can join again tomorrow, ask your questions. I'm gonna put my email over here if you want to reach out to me or contact me later. And this is it. Do we have our co-organizers online? Do you want to say a few words before we say goodbye for today? All right. Seems like they are not around anymore. That's my LinkedIn profile as well if you want to contact me over there so we can stay in touch. But I hope I will see the 50 something of you tomorrow again, please. It's going to be super fun. And now you got all this basic knowledge that you can use tomorrow. So don't miss it. I'll see you tomorrow at the same time. Thank you.
Cheers, guys. Talk to you tomorrow.